As environmental engineers, we not only need to think about the health effects of air pollutants, but we need to think about how do we mitigate those effects? How do we protect public health? Roughly 90 to 93% of your lives, my life, all of our lives, will be spent indoors. So the vast majority of the exposure to air pollutants will actually be inside. So we need to think about that, and we need to be able to model air quality and then think about how do we mitigate that exposure. So some of the sources of air pollutants include combustion processes. So for example, if you have a gas stove, cook dinner, turn on the stove, it's a combustion process, carbon monoxide, NOx, particulates will all be produced. If you smoke cigarettes, same chemicals. In addition to that, you'll also produce a number of what we refer to as PAHs, polycyclic aromatic hydrocarbons. Polycyclic aromatic carbons are fused benzene rings. They're produced from cigarette smoking. They're produced during grilling. And a number of these are known carcinogens. Some of these are potential carcinogens. Photocopy machines produce ozone. Some air purification systems also produce ozone. And then there's a whole variety of other chemicals that can produce various synthetic organic chemicals. These are produced from particulate board, plywood, adhesives used in rugs, urea formaldehyde insulation. This can result in what is known as sick building syndrome. So basically what happens is, it's most common in a new building or a newly renovated building where there is a significant amount of new carpeting, new upholstery, all of which can result in the release of these synthetic organic chemicals. They can cause many of the health effects, the acute health effects that we talked about before, mainly health effects initially in terms of allergies, eye irritate, they can actually irritate the eyes, also coughing, sneezing, etc. The other chemical that we will talk about is radon. Radon is a naturally occurring pollutant, chemical or pollutant. It's released from uranium that is actually in geological material. So from the decay of uranium, that releases radon. Radon is a odorless, colorless gas, and that radon causes cancer. So we're concerned about that. When we model indoor air quality, we need to look at air movement into and out of the building. So we talk about infiltration. So infiltration is the natural air exchange that occurs in between a building and the outside when all the doors and windows are closed. Cold day, you having go for a walk, walking to class, you notice a home with a lot of icicles formed on the eaves. Why are there icicles on the eaves? Notice other homes don't have icicles on the eaves. What causes those icicles on the eaves? Exactly, because the heat escapes easier, melts the snow, reforms, refreezes, and forms icicles. Tighter home, the heat isn't escaping, so you don't get the melting and then the icicle formation. Air can move in and out of the house, through the eaves, through the sills, around your windows, around your doors. Really depends on how well those are sealed. The amount of infiltration is dependent on the difference in the pressure on the inside and the outside of a home, and also on the difference in the temperature. Now, we also talk about the stack effect. We know that warm air rises. So in the winter, we're heating the home. The warm air is going to rise towards the top of the house. That means that it's going to pull cold air from the basement. We'll talk about this actually. It's very important in terms of radon, because if that radon is released from the geological materials in the basement, that radon then gets pulled up through the house. We also talk about natural ventilation. Natural ventilation is that air exchange that occurs when the windows and the doors are open. You open the windows, you increase air circulation, and you're getting more air from the inside, from the outside inside. Thanksgiving, a fair number of people did this where they wanted to gather, or for Christmas, they wanted to gather. They're worried about COVID. So I know a number of people that actually had their dinners with their family in the garage, opened the windows, tried to open another window if they could in order to get cross ventilation. In order to do what? Why would they want to do this? Why would they choose to have dinner in the garage, open the garage door at least somewhat, open another door in order to get cross ventilation? What were they trying to do?
To get fresh air.
Right, to get fresh air, to lower, if anybody was sick with COVID, to reduce the concentration of virus particles in the air. Forced ventilation is that ventilation that's due to mechanical air handling systems, so using fans and blowers. We can increase ventilation, so we increase ventilation. That decreases the concentration of the pollutants, but it increases our heating and cooling costs. Back in the mid-1970s, there was a major energy crisis. The cost of gasoline increased by about fourfold. Lines at gas stations were hours long. And as a result, because of that, a lot of homes that were built after that were built to be extremely tight, meaning that there wasn't much air exchange. Reduced heating and cooling costs, but the opposite was what? What happened in terms of concentrations of pollutants? So we make what we call a very tight home. We don't have much air exchange. It increases the concentration of the pollutants. So it's always a trade-off. So as mentioned, in terms of infiltration rates, it depend on the wind speed, direction, that depend on the temperature differential, the pressure differential, and also where the leaks are located. Typically, air exchange rates in a home are about 0.5, and this unit here is air exchanges per hour. So a typical home is about 0.5 to 1 air exchanges per hour. So if we have this is model the home as a box, okay, and it has a certain volume. If we have 1 air exchange per hour, then this volume of air is exchanged every hour. Very tight buildings, less than 0.5. A very leaky building can be as high as 10. And also think of the same in terms of ventilation. So for instance, sorry, in a hospital setting, especially where you're dealing with infectious diseases like COVID, recommendation is that the air exchange rates be in excess of 10 air exchanges per hour. You're trying to exchange that air to minimize the concentration of the airborne, in this case COVID, the virus, in order to minimize the potential for transmission. Now, we will model indoor air quality using a very simple box model. So we will assume that this box is well mixed. So we will assume that it is a CSTR, a continuously stirred tank reactor. Air will enter. We'll use C sub A to describe the ambient concentration from the outside entering the building. We have sources within the building. We'll look at decay. Look at decay rate constant, K. We may have sinks in the building. We have decay rate. What are some potential sources of contamination or sources of pollutants inside this indoor environment? Named a few of them before, but let's think about what are some of the sources. Your own home, what are the sources of various different pollutants? Cooking. Okay. So especially if you have a gas oven, breathing, CO2, furnace, carbon monoxide, CO2, NOx. Anything else?
In my house, we actually had radon coming up through our basement, so we had to seal that, even though you already discussed that.
So radon, we actually have a radon mitigation system also. So we monitor the radon in the basement, have it checked on a regular basis. We'll talk about radon in particular because it is so much of a problem in much of the lower half or the lower third of the lower peninsula of Michigan. So yes, radon. What else? Mentioned cigarette smoking. What are some sinks? What do we mean by a sink of a pollutant? So sinks are how it gets removed. The dust. Okay, sinks could be a house plant taking up CO2. The dust that's in the air. It's a nice sunny day. The sun, you can see the sun rays, and the sun rays you are refracting off of the dust in the air. Where can that dust go? Or how can that dust be removed? Ventilation systems can be removed by vacuuming. It settles to the floor, and then you sweep or vacuum it up. So it actually is got sedimentation occurring. We can model that sedimentation as typically as a first order rate expression, and we could vacuum it up. So those are some potential source sinks for the pollutant. And then that pollutant can leave through the ventilation system. It can leave through the leaks in the house. So we will describe the fate of these pollutants with a simple mass balance. So we can describe the rate at which the concentration is increasing or decreasing within this space. We'll describe that as then mathematically as the change in mass with respect to time. And that is equal to the mass rate of the pollutant entering. It can enter from the outside. So we have some flow in times the concentration coming into that space, plus whatever source terms are in the house, minus the mass rate leaving that space, minus the mass rate of decay. And we will typically describe this with a first order reaction, which we can then describe as K, so first order rate expression, C out times the volume in the system. Now, our mass is equal to the concentration times the volume. Our volume is constant because the volume of the house isn't, or the building isn't changing. We can take that out of the differential. And then I'm just going to change with some of the terminology because you'll see the terminology slightly different in air quality. Typically, we'll use I for that infiltration rate in air changes per hour. We multiply that by V, we end up with volume per time, which is the same thing as our flow rate. So it's a volumetric flow rate. And we'll multiply this, as I said before, typically C sub A is the term used for the ambient concentration, plus our source, minus I times V times C out minus K C out times V. Now, we can integrate this expression to find the concentration as a function of time. What we typically do is we'll divide both sides by V. So notice, V cancels in all but the source term. We will integrate this from C naught to C, and then this whole expression here from time 0 to time t. And what that will give us is an equation where we can relate the concentration as a function of time. Now, we'll start by looking at this in the simplest case. So we have a wood-burning stove in a room, single room cottage that measures 7 meters by 7 meters and a height of 3 meters. We have an air exchange rate of 1 air changes per hour. What we want to measure is the steady state condition, the steady state concentration of carbon monoxide, or what we measured. So we've measured this. We have a steady state. So here we have steady state concentration at 4 milligrams per cubic meter. Okay. Once it reaches steady state, the concentration, that change in mass with respect to time, is equal to, anyone remember? What does steady state mean?
Flow rate in equals flow rate out.
Doesn't necessarily mean that the flow rate in equals flow rate out. Okay. In order to have constant volume, we're going to have flow rate in equals flow rate out. Steady state, change in mass with respect to time is equal to 0. So there is no change within the system. There is no change in mass as a function of time. I'm going to assume that the air entering, the ventilation air, has negligible carbon monoxide and we'll assume that carbon monoxide is conservative. So if we have negligible carbon monoxide in the ventilation air, C sub A is equal to, if we have negligible carbon monoxide in the ventilation air, C sub A is equal to
0.
0. Okay. If carbon monoxide is conservative, what does that mean? Rate constant is equal to, it means it doesn't decay. So the rate constant is equal to 0. So the first thing we'll do is we'll just draw a picture of the system. So here is our room. We have a wooden stove in the middle, burning wood. Our room has a volume of 7 times 7 times 3 meters. So the air exchange rate is equal to 1 air change per hour. The concentration at steady state is equal to 4 milligrams per meter cubed. We have air coming in, but C sub A is equal to 0. The concentration leaving is equal to what? Concentration leaving is equal to what? C out. We'll assume that system is well mixed, so we can describe this as a CSTR. If we have steady state, as we mentioned, that means that the change in mass with respect to time is equal to 0. We have a source term, S, which is what we're looking for. We have I, V, C sub A, which is equal to what? I is equal to 0 because C sub A is equal to 0, minus I, V, C out, which is equal to the steady state concentration, minus K, C, V, and this last term is equal to 0. So in this case, now, the source term is equal to I times V times my steady state concentration. So it's equal to 1 inverse hours times 7 meters times 7 meters times 3 meters times my steady state concentration, 4.0 milligrams per cubic meter. So volume cancels, and I'm left with milligrams per time. So that stove is releasing 488 milligrams of carbon monoxide every hour. We go back and we could look at that carbon monoxide concentration to determine whether or not it's of concern. Questions about any of this? We're not going to have time to go through this problem, but let's try and set it up. So the question, why does C, okay, it's a good question. Why does C out equal steady state concentration? If we have a completely mixed reactor, then if we measure the concentration here, or we measure the concentration here, or we measure the concentration here, or here, it will be equal. Think about a blender. If you're making a smoothie and you add all the ingredients and you blend it really, really well, then the composition should be the same anywhere in the blender. If we have a CSTR, also referred to sometimes as the CMTR, a completely mixed tank reactor, concentration is the same no matter what. Okay? And because we said we were looking at the steady state concentration, what's happened is if we were to measure concentration as a function of time, we arrive at the cabin, nobody's been there for a couple weeks, so the concentration of carbon monoxide is negligible, just as it is outside. It's really cold. We get that stove get it working. Okay, we're burning wood. The concentration of carbon monoxide will increase over time until it's constant. It's at this point here that it reaches steady state conditions. And at this point here, within this volume, the change in mass with respect to time is equal to 0. So that's the steady state condition. Does that help in terms of explaining this situation?
Yes, thank you.
So I'm not going to start this next problem. We will start here. If you have some time on the weekend, look over this problem. See if you can draw a picture. Don't worry about solving the problem, but think about, can you draw the picture? Can you write an equation that would allow you to determine the concentration of carbon monoxide at 7 p.m. So we'll end there. Happy to stay and answer any questions that you have. A couple of the questions on the homework, there were some questions in office hours today, so I added some comments in the discussion to hopefully prompt you and help you answer those questions.
Professor, could you please just go back to the equation on the previous slides?
Here,
There was one before this as well, right?
this one.
Yep.
Any questions about what I did here?
Thank you so much, Professor.
And have a good weekend.